Welcome to this section. We are really glad to have you on this webinar. And in today's webinar, we'll be talking about the applications of geospatial data science in crop yield prediction. And we are glad to have you on board. And before we proceed, let's just talk a little bit about the hub. So we created the geospatial hub basically to bridge the skill and knowledge gap we observed in geoprofessionals, especially in Africa. Our vision is to create a nurturing community for geoprofessionals, and our mission is to provide geoprofessionals with easily accessible skills and knowledge to meet up with international standards. So we've been doing this with our YouTube channel in the past, and on our YouTube channel, we have a plethora of videos you could like watch to get hands-on special skills. And last month we launched our website. So basically, we realized we couldn't do a whole lot as we would love to do on YouTube, and we could actually do more of this with our website. On our website, we have free courses. About most of the courses are free, so you could just come to our website and take free courses. And beyond just taking the free courses, you could also read blog articles on our website and see all of our previous webinars and a whole lot more on the website. So the website has some edges. So the website basically has some edge over YouTube. And today we'll be talking about the application of geospatial data science in crop yield prediction. And this course has some dependencies, so it has some prerequisites. So one of the prerequisites is we assume you understand remote sensing, or you have a bit of you have some knowledge about remote sensing. But if you do not have this, it's no problem. Our YouTube covered, so you could come to our YouTube and go to our playlist. So on our playlist, you'd see a remote sensing playlist, and you could actually see we've actually dedicated 4 different weeks to remote sensing alone. So you could watch all of these videos on remote sensing, and you could also come to our website and take a remote sensing course, and you get the certificate for free. You could watch the course for free as well. Then another dependency for this webinar is Python. You need some additional Python so you don't get confused or lost when our guests are speaking. So we also have a foundational course on Python. This is what we did in our webinar about 2 3 months ago. Just come watch video. And also lastly, last month we had a webinar on machine learning. So we walked through machine learning. It's really impactful, and I can almost brag this is one of the best um introduction to machine learning you see outside. So it's free. You could just come and watch videos on the introduction to machine learning, and also you could also come to our website to explore the website and watch all the webinars on our website. Today, as we stated earlier, we'll be talking about the applications of geospatial data science in crop yield prediction. But before we proceed, let's talk about our guest. Our guest name is Ayomide, and Ayo is a self-motivated data scientist and geospatial developer with experience in working with various form of data. And I would like to add to that a wealth of experience. He has worked with different type of data, speech data, health data, and community data. He has a substantial record of success in data collection and manipulation, also in spatial mapping and analysis, and also in the use of machine learning, which is what he would be walking us through and today. He has also answered a plethora of projects revealing spatial relationship patterns and trends in which help organizations to make informed decisions. He has experience in using a lot of data mining tools, and a few of them are Python, SQL, and also Excel. He has been successful with data analytics. He has won a number of Zinde competitions, and he has experience in data reporting, ad hoc reporting, and he um, represents his results and insights with solutions to problems in graphical form. We'll just switch gear to Ayo, and would like open the floor to Ayo to end of the session. And we hope this session is important. So just sit back, relax, and enjoy it.
I welcome everyone to today's lecture on the application of geospatial data science to crop yield prediction. I'll be the one taking us through today's lecture. and we'll be making use of a data set from Zindi, and I'll be making reference to Zindi. Zindi is the first Pan-African data science competition platform, which hosts a lot of competitions ranging from e-commerce to agriculture to insurance. Um, so as a data scientist, if you are not so um, being particular about geospatial data science, you could try your hands on some data on Zindi. Nevertheless, we'll be working with the Siaga Crop Yield Prediction Challenge, which was hosted on Zindi some couple of years back. Um, and the competition is all about crop yield prediction from Kenya farms. The data set was collected over the years from maize farms on Kenya land, and the units were recorded. So the objective of the challenge is just that you predict the number of units that should be harvested from a particular um, sentinel imagery which you are giving, because we are also provided with sentinel imagery. So you whatever processes you want to run or estimation you want to run on the satellite image, you do that, and then you can actually predict the amount of unit of maize that would uh, be harvested from such farm. Okay, so I'll just go through the data so we could actually see what we'll be working with. So this is how the submission file will look like. You are given a particular field, and then you have to estimate the yield of that field. The evaluation metric for this composition is root mean square error, which is quite similar to mean squared error. But I think what it just does is that it's actually calculate the differences between, or will I mention like the difference between your estimation and then the precise one, the accurate one. So whatever the value is after the accurate and precise prediction is subtracted from your own prediction. That is, whatever is left is the error. Okay. So I'll just move to the data. And if we could read through this, the quality of our data varies. We have the good quality, we have the medium, and we have the poor quality. And for each field, we've been given sentinel imageries, and there are 30 bands for each of the 12 months, which makes a total of about 360 image bands. And the size of the imagery ranges from it's 41 by 41 pixel. Okay, and this is an example of what we can see here. So you've been given the data, the trained CSV, the image arrays which you have to test your model on, and then the image arrays which you have to train your model on. There, the band names, just for you not to get confused, if I attach that. And image bands also is quite similar. Then the test field, which yes, that is this contains the yield data. I'm sorry about that, not definitely the yield data, but the feed IDs on which you have to test your model on. And also you've been given some additional data such as the soil data and then the climate data, so which are also quite important for predicting crop yield. So not to waste much of our time, I've downloaded the data. Let me go back. This is the data over here. So the data have been downloaded. So we could just go to our file explorer and we could actually see the data over here, which is the image array test, which is what we have to test a model on, the image array train, which is what we have to the data set on which we are to train our model on. So all this data, the train, the test, the sample submission, all this data which we have seen on the website will be downloaded. So just try and download them. I've downloaded them already. So the next thing is to import them. Right now I'm using Visual Studio Code, and you could use any IDE you're actually comfortable with, but for now I'm using Visual Studio Code. And the next thing for us to do is to import our libraries. We'll be making use of Kfold, which is a form of cross-validation, which I'll explain later on. Pandas, NumPy, Matplotlib to visualize our imagery. Then train test split to split our data set into train and test. Then mean squared error, which is our evaluation metric. Standard scalar. I don't think we'll be needing this. Then LightGBM, which is the model we'll be using. Also LightGBM regressor, since this is a regression model, but this is still the same, but this is just being particular, so I would cancel this. Or better still, I think we need both of them, but I'll just mention this. So we won't be using random forest regressor, so we'll be using LGBM regressor. Import random, this is just to make sure that we get the same output of the time we run our code. And then we've stated our random as 42. You could name it as anything, any number you feel like. Then pprint, we won't be needing this. Cborn, I guess we'll be needing that to visualize our imagery. Then this is just to make sure pd.set option displayed on max column is just to make sure that while we display our data frame, we can see all the columns that are being represented. We've already imported Matplotlib up here, so we won't be needing that. And we've also imported NumPy. I think I imported a lot of libraries twice. Sorry about that. Now you could define your path to wherever you downloaded your data, which is, for me, I downloaded my data into this folder, crop yield prediction. So you could just copy this and then paste it here. So still the same. To copy and then paste. And then you could just put an R in front if you so much like. But wait, let me just change this since just put an R in front. So I want to load our data set. So I think the best thing for us to do is just to come here and get the names of our data. For example, I want to import train. Then I would want to import test field leaves. So I'm just getting all the names of our data first, which is what I guess we should do first. Then I'm getting the names of the CSVs. Then sample submission too. I want that. Then field with additional info. All this data were given to us on the website. Yeah, I guess that's pretty much it. So we'll go back. So the next thing for us to do is just to put this in quotes. So this would be named, I would love to name this, let me see, what name should I give it? Okay, let me give it train df, then pd.read csv, since it's a csv file. Then I'll add our path, then I'll concatenate it with train, and train is a csv, so I'll put this in front. and then I'll close that. But it seems it's a small letter. I don't know why. Okay, so the next one will be test field IDs. We just name it anything. Test field IDs. So yes, just remove this, and then we use the same name, which would be, then we just put df cost to pd.read csv. We add the path, and then we concatenate it .csv. Let's add some space to it. Then we could also take this as sample submission df equals pd.read csv. You add a path plus this.csv. To add this, add info df cost to pd.read csv, not clipboard. Path concatenate it .csv. So yes, we have our data ready. So we could run this, and then this string df we could just run it to visualize our data. And now you could see we have the field ID, the year, the quality, and then the yield. Now these field IDs, they represent different fields with just random names. The names doesn't matter. And then we also have the year each maize unit was recorded and also harvested from the farm. Then we have the quality, either good, either medium, or poor, which is 321. Then we have the yield in units. So we could just, if you are so particular about the information on in this data frame, you could want to check for the number of fields that you have. So this will be train df dot field id dot unique dot shape. So you want to see each unique, probably they are duplicate fields in your df or in your data frame, I mean, and then you are trying to visualize this unique field. So you could see we have 2,977 unique farms, which is totally corresponding with the number of rows, which is quite true. Now we could just comment this and name this number of unique farms. Then if you also want to check for how many years do we have, how many unique years, probably it's ranging from probably 2016 to 2020, we don't know, but we just want to know what unique years we have in our data frame. So we could go with train.df, sorry, train underscore df dot year dot unique. Now it's telling me we have about 4 years: 2016, 2017, 2018, and 2019. We could also, I'm also thinking probably we could count the number of um, unique quality that we have. Are we having more good quality data in our data frame, or we're having more medium quality or more poor quality data in our data frame? So we could go train underscore df dot quality dot value count. Now we could see 321. We have more good data set That is those that were taken on the right position, okay, at the center of the farm, which is quite good for us. So I think this is quite okay. This is just some analysis that we've done on our data. And then I think the next thing we would want to do is I just want to like view the pixel of the imagery, and let's see what we have here. Let's see how the imagery look like. But first and foremost, we need to define where our data is. So we know we've already defined the paths here. So we could just take this variable that has already been defined, and then we add it, and we concatenate it with the folder where the image is, which is image train. This is the folder. If you have to go and enter into this folder, there's another folder inside. If you have to enter into that folder, then you can see the images, that is each unique field. Okay, each unique field, that is these fields that are actually here, those are their imageries. But now those images are in numpy. They are saved as numpy file. So we'll still look at how we can visualize these files. So let's just go back. We'll just take this name, and then we'll come here. Let's see. Okay. Then we'll just try and, since it's double folder with the same name, we'll call the name of the folder again. So we'll just copy this and then place it here. Now we can now visualize any file we want to visualize, probably this or this or this or this. Okay. So I would just say we look for any random file, or let's just pick a particular file. So let's say we want to visualize this. So we could just say file just to this, and then need to save it in a variable. So that is it. So it could then go as fn is equals to train folder, okay, plus file, and you could print this. What we did was we concatenated these two files, or two variables, I mean, which will actually give us something like this. Let me just go up here and then copy this. To actually give us something like this, which is leading us to the name of, or the location of the file. So it should give us a full path to the file this way. So we could just print fn. So we are really sure what we're doing. Yeah, so that is it. So I will say we then load it. Okay. So this is, let's call this array mp.load fn, and then if you so wish, you could just, let me run this. So we just print fn. Let's see what's inside. So we could see these are values, these are numbers of arrays inside. And now the next thing we could do, we said we would like to visualize it. Okay, now I would say we take note of the band, because obviously this is not Landsat, this is Sentinel imagery. So the best thing to do is to search for Sentinel imagery bands and try and look at the bands. Normally when you're trying to visualize in true color, you know, if you're using Landsat, Landsat is 432 or 321, sorry, 321, which is true color. While Landsat false color is 432. Sentinel true color, which we're about to check, would be then 432. Okay, so let's just try and see what we're trying to say. We all know true color is red, green, and blue. So red, the green, and the blue, which is 432. So we could see this is actually sentinel bands. Okay, now if you have to check for Landsat, so I'm sure of what I'm saying. I'm not just guessing. Okay, so we could see red, green, blue, 321. So Landsat 8 to be precise. So since we are aware of that, let's just move back into our code. So what we're about to do now is we are trying to visualize this file, this particular numpy image, numpy file, which is a satellite image in true color format. So the next thing we do is we need to stack it together, but first we need to get the name of the file. Now if you stack this together, since we already loaded arrays, okay, we could even check for the shape, which could be ar.shape. Now this is 360 41 41, which corresponds to what we have at the top here. It says there are 30 bands for each of 12 months, giving a total of 360 bands. The band's name are provided in the band name.txt file, so you could check that if you want to. And also we spoke about the file size, which is 41 by 41 pixel. So this satellite imagery for January, for February, for March, April down to December has been stacked on just one, that is for that particular location. The satellite imagery has been stacked on just one numpy file. That's why we have 360 bands here and then 41 by 41 pixels. So I just hope we actually understand that. So we have the array here. Now we're trying to load it in true color. So you go for the fourth band and then the third band and then the second band, which is 432. Then you could actually close this p.stack, and then you need to define the axis -1. So you could actually run this and we could also visualize this. It will still be in arrays though. So what this axis does is to switch it. It turns, like it flips the array. I could show you a quick example right here. You have to go to numpy.stack. I had opened it before, so just to show us. You have to check this example. We have a b is equal to np.array 1 2 3. This has just been generated. It's just a random data that has been generated. And we have b is equal to np.array 4 5 6. Now when you use the function np.stack, numpy function np.stack, it will give you the same way it is without defining the axis. Now the axis could either be 0 or it could be -1. If it is 0, it will be the first dimension, the way it is. And if it is -1, it flips it. Okay. So np dot stack ab, if this was given as axis equals to 0, it will give you the same way. That's the default. Okay, but immediately you see it has been, it was axis equals to -1 was defined. You see it's flipped it, so we have 1 4 2 5 3 6. Can you see? So that is the function of that's the function of axis equals to -1, which we already can see here. We can see that the dimension has changed compared to what we have here. Okay, so now you're trying to normalize the data, because most times the way we normalize our data, or most times our images comes within the range. You some at times you could see some images within the range 0 to 255. At times you could see some within 0 to 1. At times you could see some -1 to 1, depending on how the image was normalized. So here we are trying to normalize our data, and what we are trying to do is to divide every pixel in the data by the maximum pixel. Okay, so what we could do is RGB jan, which is our array, equals to RGB jan divided by mp.max, as you are trying to look for the maximum or the highest pixel value. So you input this also. So now you can now plot it using imshow and then RGB jan, which you then see that would give us um, our imagery, which is in true color, though it's a bit blurry because of the resolution and all. But I hope you don't understand. So you could play around this. You could pick another file, could input it here, then you could run it to give you another image entirely, as we can see here. So you could play around. If you want to go for another band combination, let's say 5 4 3, then you could run this. You see, so that's the way it actually works. So one thing I'd like to show us is how to, probably you're trying to like check, variation in, we just delete this since we won't be needing it. You're trying to check some variations in I think we already did this up here, so I'll delete this. Some variation in the imagery, probably within the year. So you could actually view for 12 months all around. And I told you that the images of all those 12 months have been stacked on a numpy file, which is what we have here. When I showed you the file size, you have to check for this also. When I show you the file size, or better still, the file shape, you see 360 for each month. That is, when you say 30 times 12, should give you 360 bands times each month. That's why we have 360. Then 41 by 41, the size of the pixel, the size of the numpy file, that is of your imagery, the way it was taken. I hope I'm not getting us all confused, but I hope you all understand what I'm trying to say. So now we could do a plot. We're trying to actually plot for all 12 months. So we could say PLT, which is matplotlib subplot. We'll be using subplot. Now you could do any way you want it. You could say 112 or 111. Let me see. Okay, we could do 4 3. 4 times 3 will give you 12. We could do 3 4. 3 times 4 will give you 12. 6 2 will give us 12. So if you are not familiar with subplot, let me just show you. It's you can actually plot a lot of images on or will I say a lot of subplots on a particular plot. So while that is loading, let's just continue with the code, and then you can determine the fixed size, which is the size of the major plot, how you want it to be like. So here we could actually use let me say 1512. Face color, All these are not really necessary though, so don't let me have this. They're not really necessary. But if you just want to know more about it, you could. I don't know why this is still loading. I guess it's the network. You could just go into Matplotlib documentation and then read more about subplot. So we have fig.subplot adjust. Now this is just to determine the space, the horizontal space and the vertical space between each subplot. So let me give this comment. Let me give this 0.1. Let me give you 0.12. Then we have the axis. Here we only define for the figure. Now let's define for the axis. Cos axis dot ravel. Don't know why I'm finding it difficult to type easily. Now if you have to print this, let's run this. Now you could see the subplot. We could see we have 6 by 2. Now if you want to make this easy to read, you could say 4 by 3. So it gives you in 4 vertically and 3 horizontally. So just to make it easier to read those values surrounding it, let's just make this 0.5 and let's see the effect it has on the subplot. Okay, fine. I think this makes more sense. Okay, great. So yeah, I think this is good. Then we could just begin plotting our imagery on each of the subplots. So for I in range 12, now remember it's 12 months, and when you run a for loop this way, it start counting from 0 in Python. So you could say print for I in range 12, print I. So let me just show you how that works. And you can see it starts from 0 and it ends at 11. If you have to count all these together, this is 12 numbers. So the next thing to do is to actually stack them, because without stacking you can't actually visualize it in either false color or true color. You have to stack those bands together. So also remember that we are looping through each year. Okay, so 0 would mean for the first array in the numpy array, since all month have been stacked on an imagery. So we are actually trying to visualize for each month, so we need to loop through the array in the numpy file. So for the first loop, I will be 0, which is the first array in the numpy file, which is for the month of January. So times 30 plus 8, which is the band. Okay, then we have array I. We're trying to visualize for, okay, let's visualize for true color, which is 4 I times 30 plus 3. Then we could say array I times 30 plus 2. And remember what we used there, we used axis equals to -1. Now RGB is equals to RGB divided by np.max, if you still remember RGB. Okay, now let's do plot.imshow. But if we have to do plot.imshow, it will only plot, like, it won't plot on these properties that we've already defined. So we need to use axis, which is what we already defined. We need to use axis I, that is for each subplot. it should look through it. So axis I for the first subplot, this one, the second subplot, this one, the third, the fourth, the fifth, like that, till it gets to the 12th one. So this is imshow. So remember, normally it should be plt.imshow, and then you fix in probably RGB Jan, which is what we had before. But now, since we already defined for axis over here, so that is what we are trying to plot on each subplot. Then we have RGB dot clip 01. So you could actually read more on clip. I know we have a lot of variables here that we're trying to define. So yeah, this is already done. So you could see this utility wrapper makes it convenient to create common layout of subplots, including the enclosing figure object in a single call. So you see, we define the figure and the axis. AX can be either single axis object or an array of axis objects if more than one subplot was created, which is what we actually did. Okay, now if you are trying to create more subplots, you could see we used fig and axis, which is what we used over there in our code. All right, now I was about showing you, let me see what other variable we're about defining before I stop. I think that was face color. Let me see. Let me go back to the code. lt.subplot. Okay, let me just search for it here. lt subplot face color, yeah. So here we could see face color. Face color should be a variable. Face color, yeah, I think that's right now, yeah. So it's actually a variable, or will I say a property if you're trying to just, add more visualization effects to your subplot. Then let's move to dot clip Python, or better still, let me say imshow dot clip. So let's see what that does. Should be a dot clip. Better still, let me write it in clip imshow. All right, great. So what it does is actually clips the data ranging from 0 to 1. So that's what it does. Now you have to go back. Let me point this out. If you have to go back and then you have to run this code, fine. And then you should take note of RGB after we've divided it by the max. So if I have to come here and then I have to say RGB, I want to see the values in RGB. You could see 0 0.6, 0 0.4, 0 0.4, what other value? 0 0.5. So what we're trying to do is that all I want is values ranging from 0 to 1. Okay, that is what I want to see. I don't want no other number, and that is what you should visualize. Okay, so axis I dot set title, you're trying to set the title for this frame. Okay, so you could actually put a string here and then just look like this. You want to see, okay, this is for let me see, let's do this way. This is for the this is for months. You could do this way, string, then I. So this will tell you this is for month one, this is for month two. You know, month one is January, month two is February. So why I'm adding one here is because of it to start counting from zero. So and you don't want it to start counting from zero because there's only like month zero. So month one, we all know month one is January, February, March, April. Now you could run this. So I guess let's just put a bit of space here. Yeah, cool. So now this is for month one, for month two, for month three, month four, month five, month six, month seven, month eight, month nine, 10, 11, 12. Now we could see the variation in how the images are. All right, now we could see the variation in it. You could see like probably some crops are like the chlorophyll content in the crop would definitely vary over the month. So you could actually visualize it this way. We could also use 543 so as to look at the chlorophyll content in the crops. So the more red it is, the higher the chlorophyll content in it. So yeah, so that's just it. So that's actually how to visualize your imageries. So I'll just delete this. And now we're about viewing the band names. As is, we want to actually look at what band names were we given. Okay, since yeah, this is the file. So we could see 0s2b1, 0s2b2, 0s2b3, b4, b5, and b6. Okay, so I will just go back into the code. Yeah, I'll just define this as band names equals to L dot strip, which is to strip the white lines. Okay, for L in open link plus band names.txt because the band names is a txt file. Then you are trying to read it, you are not writing to it. Dot read lines, you want to read each lines. Okay, now open link, I don't know what link isn't defined, so better still, let's just say path plus band names, because that's the path to where band names is. Okay, so we could see we have OS2B1, OS2B2, OS2B3 according to what we saw in the .txt file. Okay, so I think it's taking much of our line, so I'll just put it that way. So now, so as to save us a lot of stress, I would like to remove those bad quality data. Which is equals to, I don't want it to be equals to 1 because I don't want to like give my model much stress trying to figure out the best way to predict the yield per unit. Okay, so because these are erroneous values, okay, and I don't want them to corrupt my model at the end of the day. So the best thing for me to do is just to remove it off, look for another way around it, around the problem for me to use this data. But since it has been mentioned in the description of the data that these are actually poor data, so I don't want to use that. So I'm removing that, and then what I'm left with is the good data and then the medium data. So you could run that, and you see we only have 32 left in our data, which is the good and the medium data. So now I want to specify my band of interest and the center point through which I'll be working. So I want to specify my bands of interest. Now, not all bands are actually quite okay for or quite suitable for predicting crop yield. And also, we would like to specify the point where we'll be picking our pixel values because, like I mentioned, the data set comes in various degree of quality, such as the good, the bad, and the medium. So now we'll be taking away the bad, which we've already done. Now, because we know we don't want to start or we don't want to use all the pixel values on the images, but we want to like take a pixel value that will represent or that will represent more of what is on the field. So we want to take it from the center point of the satellite imagery, which would be something close to like 20, that would be 20 by 20, which will be in the center. Remember, we said the satellite imagery is 41 pixel by 41 pixels, something which is close to the middle of 41. That is the center point of 41 will be 20. So we'll be using 20 by 20. So now I want to create a function that would help us specify the bands of interest we'll be using and also only pick the center pixel value of those bands of interest. Remember, the numpy image we are using, or the images we are using, I mean, have been fixed. They've been stacked onto a numpy file. So we'll be working with that numpy file. So now I'll be creating that particular function that will be helping us extract those pixel values at the middle of the imagery. So I'll call this process in, and then I will specify the file, which is FID, that is the file ID. If you are to actually check your train.df, better scorn.df, which is your data frame for your training data, for training your data, that is the data frame for the train data set. You see we have a field ID with different field IDs for each field. Okay, so this FID is this what's it called? This FID are these random field names. Okay, now we also need to specify the folder which will be picking our data from, and we could call this part plus. Remember, our part is a defined variable, which is this. So obviously yours will be different from this or could be different from that depending on where you save your file. Now remember, it's inside a path, which I'll just copy, but let me show you first. This is crop you, then image arrays train, and if you enter into this folder, there's another folder here called image arrays train, then before you then meet the files. So we are trying to copy these two guys here, so I could just come here and then copy this, and then I replace this. Okay, let me just change the format it is. Okay, so I guess that's good. And remember, it's a function. So now the next thing we have to do is to define the folder together with whatever file ID we'll be using. Okay, so you will just call this folder since we already defined this over here. Okay, so if you are to print folder should be something like part plus. So folder, of course, if the way this is, let me just print it so you see. So if I say print folder is equals to part, okay, sorry, let me just do it this way. I think to make more sense this way, then say print folder. Now you see the part how it looks like. So this is what we are trying to generate. Okay, and let me just remove this since we already have it in parts. Let me remove this thing. Okay, so this is how it would definitely look like. That'll be folder. You want to concatenate this with the name of the file, which will be FID. Okay, which is what we have up here. Then concatenate this with .mpy, which is the file type. Okay, the mpy. Okay, and now sorry about that. And now what you want to do is you want to load the array just like what we did there. That will be np.load fn, which is the file. Whatever file you pass would, would definitely be coming from this folder, and then you need to load it using numpy. Now the next thing for us to do is to specify our band of interest. Okay, let me just load array. Okay, specify band of interest. No, we're going to call this bands of interest. We're needing like I said, not all bands are actually um can be used for crop yield prediction. So we'll be using band 11, Sentinel 2 band 11. Now you could just go online and then search for the importance of these bands. You can see band 11 here. It's shortwave infrared, 20-meter resolution. The wavelength is about 1610. So we'll come here. We'll be using S2 underscore B11, then S2 underscore B8, then S2, sorry about that, S2, which is band 8 underscore band 5, then we have S2 underscore band 3, we have S2 underscore band 2, we have climate variable 2, which is clean PR. I don't think I'm writing all this from my head. Of course not. They are actually here in our variable. So it depends on you, whatever research you've done. But with the little research that I've done, I think these variables are quite okay. So you could further make some researches. Sorry, you could further make some research on which variable are actually okay. These are some climate variable here. We also have some soil variables that you could also use, you know. So yeah, but I'm quite okay with this. So then you want to look through the months. Okay, and remember Python start counting from 0, so this is definitely 12 months. Now you want to create something similar to this. The way these are, you want to create something similar to that using Python. So it will put the underscore there itself and then look through the years, or through the month, I mean. So it will be 0, for example, we will have 0s2b11, 0s2b8, and like that. Then it comes again 1 underscore s2 underscore b11, 1 underscore s2 underscore b8, something like that. So that's what we're trying to create. So let's say bns equals to string month. Remember month is, sorry, this should be this another. Remember month is an integer, so that's why we are trying to like add string to it so as to string, it's convert it to a stringify, if there's any word like that. So then you concatenate it because you're trying to like make it something similar to this. So let me just copy this. This will be the first one that we'll get to see. So let me just put it here and then comment it out. So 0s2b11, so the first one will be 0. So then I'm trying to stringify underscore, this underscore here, then you can then add your band. So I'll say b for be in bounds of interest. That is, you are trying to look through this list here, which is band of interest. So I could just comment it and say stringify, there's any word like that, stringify the band of interest together with the months. Okay, so yeah, so the next thing we want to do is we actually want to pick um, the location of each of these string. For example, let me just comment this out. It might seem a bit complex, so let me just simplify it. Let me come here, and then you see for month in range 12 BNS bands of interest. Now this band of interest is not defined because it's inside this function. That's why it's saying it's like there's this line under it. So what we could just do is just to come here, copy this out, and then make it defined here. So it's quite okay now. So we could just print BNS, and you get to see, and you could get to see this is what we are trying to create. Now what the next line of code I'm going to write here is actually trying to pick out the location of these particular names in bound of names. So for example, this is location 0. Okay, this is location 0, this is 1, this is 2, this is 3. Remember, Python start counting from 0. So that's what this next line of code is about to do. So idxs equals to mp dot where mp dot is in bound names, okay, comma bns. That is, wherever these particular names are in bound of name, you should take out those locations, their locations. Okay, now what should we do with that location? It should then add those location. Okay, you should use that location of those particular band names. Okay, and then we are looping through each array, each field IDs. Then take for that particular band of that particular, remember this is the month and then the band. So for this particular month and for this particular band, pick out the center pixel. That's what you just did here. Pick out the center pixel. Pick out the center pixel. So I'll call this for names, look, or better still, locate the location of each band in band names, which is that txt file. Then now get the center pixel value for each of the specified location, which is the bands. Okay, okay, now we need to save whatever result we have into probably a list or a dictionary or something. So let me just go up here and then define a dictionary that we'll be using. So this is an empty dictionary called values. So now we'll now loop, because we want to actually, like, we want to have something like this. Okay, for example, what we actually did here, I'm coming, what we actually did here, we are trying to, like, okay, let me just use an example for you. Let's say we have or let me call this one first set, or better still, let me say this is the bands, and we have 1, we have 2, we have 3, we have 4, we have 5, and then this is the pixel value. Okay, pixel value, let's say we have 20.2, then 40.3. I'm just using this one for example. 50.6. okay, 90.3. how many? 1 2 3 4 1 2 3 4 5. 70.3. 9. Okay, now what we are trying to do is you're trying to loop through it. So let's say for bands, or let me say BP in zip bands pixel value. Okay, now print BP. Now you see that each bands would align with this, meaning let's say for example in band 1 for, let's say band 1 and for months, let's say this, let's call this bands for month January, let's just call bands January. Okay, so let's say this is for band 1, band 2, band 3, band 4, and band 5. These are all bands for January. So let's say the pixel value for band 1 in January, that is the center pixel value, was 20.2. The one for January for band 2 is 40.4. For January, band 3 is 50.6, something like that. Now you want to like assign each one of them to each one, so that when I'm looking at it probably in a table or something, I know okay, this is band 1, and when I'm about to trace it, I know okay, the center value for band 1 in January was 20.2, the center value for band 2 in January was 40.4, something like that. So if you print this out, you see it has already assigned it. One for band 1 20.2, for band 2 40.4, something like that. But now you want to put it into like a dictionary or list, so that you can save it probably onto a data frame. So we could call this dict info, which is an empty dictionary, and then you come here and then say um you could say dict info, because you are trying to assign values. B is equals to P. So at the end of the day, when you're done with the loop, you could just say dict info and then print dict info out. And then you see what we have. Now you could see 1 has already been assigned to 20.2, 2 has been assigned to 40.4, 3 50.6, and so on and so on. So that's what we are trying to do here. So we are trying to, whatever value we have, that is for each month, for each band, and for each band, okay, we'll now assign it to the center value, which is what we need to calculate our vegetation indices, and then we assign those values onto a dictionary, an empty dictionary. So it will be something like this. So that's what we are trying to do here. So we could just, example of what we did here, we could just do it over here. So which is for BNS, and then, or we could just call this anything, it doesn't really matter. Let me call this B and N. For B and N in zip BNS V0, or better still VS0. Okay, so um values, okay, B is equals to N, which is probably very similar to what we did here. Can you see? Dict info B is equals to P. So at the end of the day, we'll be having something like this. Okay, and then you could just return the values when you're done, which will be the dictionary. Okay, so I guess we are done with this particular function. Okay, so you could just run that function. So it's already saved as it. So let's just cancel this. Now we now want to use this function that we've created to create our data frame, which we'll be using. So I'll call this data frame train sampled. So whatever value that has been assigned to this dictionary, or whatever values that are inside this dictionary, I will now assign them to this train sampled, which will be a data frame. So it's an empty data frame at first, then it will be filled with values using this particular function we created, which is process in. Okay, and I'll stop process in, and I mentioned that we'll be using FID, which is the feed IDs. So what will be happening now is we want to look through each feed ID in our train DF. That should be underscore. So we want to look through each FID 1, 2, 3, as many as 2,976 in our train DF. Okay, so this will go as for FID in train DF field ID, this column here, you just copy and paste it. Okay, dot values. All right, so that should make up our train sample. So what we'll be having next is those middle pixel values, and then the name of their columns, which would be this guy. Okay, so if I run this, you should have a data frame. So it might take a bit of time because it's actually, extracting the pixel value, center pixel value of 20 by 20 pixel. So I'll just delete this cell over here, and then we could just wait for some few moments. So the next thing we want to do is to do a bit of feature engineering. So let me delete this cell since we won't be needing it. So while that is running, let me just run through feature engineering. So we can create a lot of features, okay, using feature engineering, because this is more like predicting crop yield, and crop yield actually matters, or I would say when it comes to crop yield, chlorophyll content of plant matters, the water content also matters. So for this data, we already have the pixel values, that is the middle pixel values, which are these values that you are looking at, and which is what we'll use in creating our next features, which are vegetation indices. Now, if you notice, the number of rows are not the same, and that is because of we already removed some bad qualities away. Okay, so let me just go on, and then we have a lot of columns here. We have about 84 columns, which are 84 different bands for each month. So OS2B1, this is for January. Anywhere you see O is for January. Anywhere you see 1 is for February. Okay, so I'll just delete this empty cell, and then we'll come to vegetation indices. Now we're about creating vegetation indices, and we'll create it for all the whole months from January to December. So I could say for I in range 12. Okay, now train sampled, which is our training data set. Okay, train sampled for NDVI. This is NDVI, which we are trying to create, and normally the formula for NDVI is NIR minus red divided by NIR plus red, which is band 8 minus band 4 divided by band 8 plus band 4. So plus, you can just name it anything, NDVI months, anything you want, string I, but this is the way I want it. So this is NDVI month 0, which I already know is January, the NDVI month 1, which is February. Okay, now band NIR is band 8, so we'll be using band 8. So you could just go through your data frame, and this is band 8, but since you are doing for the whole month, you can't just pick one column like this, because that will be only be for January. So you have to write it in a way such that you are picking from January to December, and the only way you can do that is to write it this way, in which I'm trying to write it. Though you might find another way to write it, but this is the way I want to do mine to make it simpler. So that's string sampled. So you're trying to look through each string, and the easiest way to do is just to use this way, then plus, since every of, even if it is for January, for February or March, it will be S2B8, but this is the only difference that will be there, the 0 or the 1 or the 2. So which is already what you're trying to create here. So when you look through it, for I in range 12, the first one will be 0, the next one will be 1 for each loop. So this will be S2B8. Okay, so minus, this is NIR. I've already band NIR, which is band 8. Now the next band will be band 4, which is band red. So this will be minus train sampled string I plus S2 underscore B4, right? So this is it. So you could just copy this and then press divide and then put this, okay? And so that is it. So, but do not forget, this is minus, and this will be plus. It is band 8 minus band 4 divided by band 8 plus band 4. So this is your NDVI. So when you run this, it says type object is not subscriptable. That means there's a mistake somewhere. Coming. Should be an underscore. Should be string I. That's where I made a mistake. Another mistake. The above exception was the record of the following OS2B4. Where is that? Let's need to look at each line of code to be sure we did it right. Okay, now I see where the mistake is coming. Okay, it's definitely not here. This part is correct. Okay. Mhm. Yes, 2B4. Where's 2B4 not here? Oh, I didn't think we defined before. Okay, that's the problem. We didn't define before. So B4 is not in the data frame. Sorry. B4 is not here. So let's input that. It should run now. That was my mistake. Sorry about that. So we need to run this back again. So this should work now. When this is done, this should work. Quite sorry about that. So because of our time, I would I won't be taking us through this, but we could just go through this ourselves and then do this ourselves using the example I made for NDVI. So I'll be jumping all these parts and then moving on to how to split our data set into train and test. When that is done, it's going to take some while. I think we can wait. Okay, fine. So now you could see it already ran. So you could even actually check it. Let's check it. Train sample, because that's the data frame we were using. Now if you had to come here, to scroll down, you should see NDVI, which you see here. So this is NDVI for month 0, which is January, month 1, February, month 2. Okay, I think there's a mistake somewhere. I guess so. We didn't change this. Sorry about that. So because I was seeing the values were all 1.0, 1.0. So That looks quite wrong. So yeah, so this is it. NDVI ranges from -1 to +1. So this is what we have here. Now month 0, month 1, month 2, month 3, and so on and so forth. So I'll just delete this cell and then I'll move down to how we can split our data set into train and test. Now, because of course you want to first train on your data set, see how it performs, then before you apply it onto the test data sets which you are provided with. Okay. So now what I'm trying to do is that if you notice on our train.sample which we generated using our function, okay, you notice that we don't have the feed ID here, okay, and we'll be needing that feed ID. So what we can do is to actually get those feed ID from our main data frame, okay, which is train df. So we could just get the feed ID this way, dot values, okay. Come here, I want to check something. Train df dot shape must be the same shape, okay. Yes, that's correct. So or else it won't work. Then I want to get the yield value too. When you run this should run. Okay, I'm thinking this is because it should run. Yeah, that's working already. So if you check train sample now, train sample you have the feed ID and then the yield ID. It will definitely be down. So let's just slide down. As you can see, the feed ID and the yield are already attached to the train sample which we generated. Now you could split your data using the function called train test split. And I'll show you how that works by going on to sklen. It's an sklen function. So let's just copy this and move here and say train test split sklen. And then you see how it works. This sklen documentation. Now it says it splits arrays or matrices into random train and test subsets. Quick utility that wraps input validation and next shuffle splits. An application to input data into a single call for splitting. Now it has parameters. The test size, you can determine your test size. Probably you want your test size to be 30% out of 100%, so your train set will be the remaining 70%. In random state, you want to like control the shuffling. Okay. You can also pass if you don't want to shuffle your data or not. You stratify means if you want the same percentage of class labels. That majorly has to do with classification. Probably you have ABC and probably you have more of A than B than C. So you might want to stratify so the same amount of A and B and C are in the number of splits that you have. So yep. So we're using train test split. So I'll just remove this. So one thing you could define is XY. Your X is your train data, which are the dependent variables. Y is the independent variable. I hope I got that right, but X are the variables which you use in predicting Y. That is, X are the like your NDVI, your EVI, the pixel values you are picking, and then Y is the yield itself. So say train sample, and what I'm trying to do here is I just want to I want to take away the yield and then the yield and then the field ID. That's what I'm trying to do here. So -2 means I don't want the last two columns. Okay, that's what I just did. And this is the yield. So you specify the yield So now we want to use our train test split. So this is train for training, then for testing, then the the y variable, which is the yield for the train set, okay, and then for the testing set, okay. So we'll use train test split, and you just input your y and your x. So look at this. Before I run this, let me comment this out. Xy is equals to this. We are trying to remove field ID and yield, which are the last two columns in this train sample data frame, and train sample yield, which is this y variable. Okay, so now if I run this and then I say x, I only want to see x. You see that we only have the columns, and the field ID and the yield ID are not part of those columns, which are the variables which we use to predict the yield. And then if I press Y, you see it's only the yield that is here. Okay. Now using our train test split, that would do the magic for us. Now you remember those parameters I mentioned, so you could assign those parameters here, and then you could also say you want the test size to be about 30% or 25, or let's go with 25. So you could say 0.25, and then you could run this random state. Sorry, that should work. So now if you want to see what we have, X train test speed has helped us in splitting our data. So we have about 1914 rows. Yeah, I remember we had about in train sampled, let me check how many rows we had. So you see we had about 252. So if you subtract 252 from 1914, we have about 638. So 638 will be what we'll be testing our trained model on. Okay, so if you check X test, you see it should be about 638, which you have here. Okay, so it's as simple as that. So now we want to fit our model, and I recall we said we'll be using the LGBM regressor. So sorry about that. LGBM regressor. So we're using estimate of about 1000. Okay, now we could take that model. I imported this. Why is it getting on the line? Okay, sorry, I didn't import it. So that'll be import LGB, import slide GBM. That's LGB. Great. So that remodel dot fit xtrain underscore x test. Okay. Oh, sorry. Don't let me get you confused. You could actually check uh, for the fit. You could actually just hover your mouse over the fit and then check which parameters you'll be inputting next. So you see x, then you see y. So that will be x train and then y train. Which is your x and then your y. Okay. And then you could also add your evaluation set, which is called eval set. All these are parameters, okay? And this is the x test and then y test, which are the variables we defined up here. And then your early stopping rounds too. It should be as a list. And then your early stopping rounds. And what that does is it helps stop your model from training after it has gotten to for about 100 more estimations. If your model doesn't improve, it stops training. So if this is about 200, for about 200 more estimations, if your model stops training after 200 rounds, it stops. Or if your model stops improving, that's the word. Sorry about that. If your model stops improving after 200 more rounds, then early stopping rounds help you stop the training. So let's just make this 100. Now we can print our score, which is RMSC, root mean square error. Okay, and this will be mean squared error. Okay, y test. Sorry about that. Don't know, I've been missing underscore lately. Model dot predict x test. Okay, and then you have to put squared is equals to false, because you're not squaring it. Its root means square. So um so let's just run this. It says key error 0. Any mistake anywhere. String about set. Let's predict x test. Squared is equals to false. Go through it and see if there's any mistake anywhere. There's a mistake here. If you like, you could actually put it in a list or not. This should work. So at score, you see early stopping rounds, best iteration is about 2.1554. So if you were to go up, you could see for about, let me go up a bit. L2 2.15. Okay, let's go. That's 2.15. That's the best. So you could see this is the list. It was coming 2.15, 2.16, 2.15. Then if you notice the score, the RMSE score is supposed to reduce, but now it's not increasing. This is 2.2. This is 2.3. Okay, so the best, that's what early stopping round is for. After you notice that the model stopped improving, it stopped. So the RMSE score is around 1.468. Okay, then let's just use that on our model and let's submit. So if you are to try and use the function we defined the other time, when we're talking about cross validation, we have to use the function we defined the other time in getting our train sampled. We have to use that function, which is pd dot. Okay, the function comes this way: process in and FID. That'll be for FID in test feed ID df. And we could just check that data frame and see what it consists of. What's the column name? Like field ID. Okay. Values. Okay. So, but remember that they are not in the same column. Okay. The same folder, I mean, not column. So, this part here, you need to change that part. So you need to define the part. You have to come here where we took, or where the test array test is the image for the test is different from where the image for the train is. So we'll define that part and come. This is just copy this and then scroll down here, and then we'll define the folder equals part plus. So should be image test since it came twice. Okay, and then yeah, this should do the trick. Test sample. And then we'll see it will pick the center values for the test images. So while that is running, we could just get our predictions, get model predictions. Okay, now we have for the test right here. These are the center values. Okay, so we could just, but remember we've not calculated the NDVI for it, for the test value. So you could actually write a function to help you do that. Put all the indices you want to calculate into a function. So you could just come here and then say this will be, instead of train, this will be test. And that's the only thing you need to change. Test, 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 and test. Since we are generating for the test data set, which Zindi gave us to predict on. Okay, so you could just run this. Oh, sorry, I'm running for test again. But I've already run this for the indices, vegetation indices. Vegetation index. You could say NDVI. Okay, so if you want to check it, you can check it, and then you just come here and say test sample. Okay, then you run this. Then you could actually come to this area. I'm trying to swipe this. Come here. Okay, now you could see the NDVI for each month. Okay, so now you could get your model prediction. We just call this predict is equals to model. The model we define in which we use in training dot predict test sample. Okay, and then you could just run that. So that is done. So you could check your predictions. These are the predictions. Okay, and then the next thing you want to do is that you want to store them in a data frame. So you could come and say SS, or better still, I call that sample submission DF. Okay, and then you want to create a column inside it called yield, and then you want to assign these predicted yields inside this column in this particular data frame. So you can actually run that, and then you can actually see what it looks like. Sample submission. Sorry, let me actually do this. Say sample submission df. Now you could see the yield for each of these feed IDs. Okay, now you could just, let's just make a submission. Let's see. So you could say dot to CSV. I'm trying to create a CSV. Okay, and then let's define the part which we already have, plus I could name it anything, something like our submission. Let me name it that dot CSV. Okay, and you want to put index cost first because you don't want your CSV to have any index. So you can run that, and let me move into the folder. You should have something called our submission. Yeah, this is it here. Then the next thing for you to do is to move into Zindi and make a submission. So you come here, you want to get a score because the completion is already closed. So you're just trying to see what you can get a score and then see what your model looks like or how it performs. So you can enter into this and you enter into, click on this, and then you press enter, and then you get a score. Let's see what it looks like. So our score is around 1.7506 and those who want the competition how they are score around 1.60, so I won't say it's quite bad. It's not that bad, is it? 1. I think 75, right? 75. So let's see where 75 is on the leaderboard. 75 is probably top 100 or so. Okay, we are actually using the private board. Ah, not the top 100, probably top 150. Okay, I can see 75 here. Okay, like, at least how many people enrolled? About 195 active, 758 enrolled. So I think we are not doing that bad, even with just an index, which is NDVR, which was what we used. So we could actually create more features. Like you could try your hands on using create your own index using these examples I made, then Savvy, then Avi, and green chlorophyll index, and then try out your luck. So that is how we can actually use that is actually the application of geospatial data science in crop yield prediction, and I hope you've learned one or two. Thank you.